So as Devin said, I'll be talking about the DSPy framework. The title of the talk and also the corresponding research paper is Compiling Declarative Language Model Calls into Self-Improving Pipelines. This is joint work with a lot of folks at Stanford NLP, as well as Berkeley AI and other folks. And this is all open source, of course, at DSPy.ai. So the context of this work is that through our research and lots of the research that the community is doing and lots of the exploration that the open source community has been doing, it's become very clear that we can actually build good, reliable systems with these new artifacts that are language models. But importantly, this is conditioned on us adapting them as well as stacking them well. And really the second part here is key. So if you've been following this space, you would see that there has been a tremendous amount of prompting techniques being proposed every week. Things like chain of thought, let's think step by step, retrieval augmented generation, agents, program of thought, self-refined, all these keywords and names that are being proposed in the literature and that practitioners are adapting in all kinds of applications. At the same time, these techniques are not being applied in isolation. In order to build high-quality systems, what we're increasingly seeing is that people are stacking language model calls into bigger pipelines in order to build sort of end-to-end systems. So 3 years ago, we built this Bayesian system, which answers complex multi-hop questions by fine-tuning a bunch of language models and retrieval models in this complex pipeline that I have here at the bottom. And the details of the pipeline don't matter as much today, but what matters is that increasingly and in all kinds of tasks, we're seeing such pipelines pop up. So DynSQL is a different cool pipeline that works on text-to-SQL generation. And as you can see, it has all of these stages and pipeline steps in which it will invoke a language model or interact with a database. And RAR is another one from Google, in which they sort of adapt a bunch of language models through prompting and interactions with retrieval in order to generate text and then ground that text and fact check it in order to make sure that it remains faithful to documents in the collection. So the cool thing in this space is that when we're building pipelines like this and building systems like this with these sorts of techniques, there's a lot of potential for modularity. In principle, it's conceptually very clear to say, I'd like to do chain of thought with few-shot prompting, and I would like to use retrieval in the loop. So I want to do this with RAG. And maybe when I'm building my examples, I want to use challenging negative examples. Conceptually, to someone who works in this space, these few words are almost well-defined. We can conceptualize what these things mean. But in practice, in order to convey these sorts of structures to a language model, it is pretty tricky. You need a lot of prompt engineering. And the reason for that is that language models are pretty sensitive to how exactly you instruct them to do things. And the message of my talk is that this gets a lot trickier when you're building pipelines. You're no longer trying to convince the language model to solve your task. You're instead trying to interact with it such that its outputs are predictable enough to be inputs to other stages in your pipeline. And you really don't want to do this by hand. Despite all of that, if you look at existing research and a lot of open source frameworks that are really popular, they currently are based entirely on the notion of string templates. So someone sits down, writes this long string in which they sort of say, all right, I'll have some string variable interpolation here that inserts some inputs from whatever earlier stages of the pipeline are there, and I'll sort of try to coerce the language model to give me the right output by being very subtle about how I say things. The problem with this, as you all know, is that it's super brittle, and in addition to that, it's not scalable. The language model changes over time, your prompts break. You want to plug your module into a different pipeline, it doesn't work so well with the new components anymore. You want to let it interact with new tools. Maybe a new retriever comes out, or a new database has a slightly different SQL flavor, and now your pipeline doesn't work as well anymore. And examples of this are everywhere. I have this sort of long prompt from a popular library for interacting with and chaining language model calls. I have these snippets from research paper appendices and GitHub releases. So this is kind of the pervasive way we are doing things now as a community. And what I want to say today is the DSPy paradigm is different. It says, let's program, not prompt language models. So let's sort of dig deeper into what that new way of thinking entails. Our goal is to shift your focus as a developer or a practitioner in this space or a researcher away from tweaking the language model itself or the language model prompts and into good old software engineering and good overarching system design. And in particular, we'll achieve this by treating the language model as your device. If you're working right now in typical sort of deep neural networks, usually you assume in your mental model that you have a CPU and a GPU, and there's sort of nice abstractions, things like PyTorch, where you could just sort of say, I want to have a matrix multiplication, or I want to have a linear layer, or a convolution layer, or an LSTM, or whatever it is. And you can sort of start stacking these, and conceptually, you're working on a much higher level of abstraction than sitting down and like writing CUDA code, let alone like program manual instructions for your device. In exactly the same way, we'd like the language model to be a third device that you can access in your programming. And we want to do this with an abstraction similar to deep neural networks, which is sort of an area that has been highly developed and has a lot of similarities to the pipelines we build with language models. And in order to do this in DSPy, we introduced just 3 simple concepts. These concepts are, instead of writing handwritten prompts that are long, lengthy, and brittle, you're going to specify natural language type signatures. So these are simply declarations of the behavior you expect, as opposed to specifications of how it should be achieved. So this is going to focus on the what and not the how. A very nice common sort of declarative motivation here. To use these signatures and to make them useful, we're going to give you and allow you to build your own modules, as opposed to prompting techniques, which are these conceptual things that need to be mapped into prompts. We're going to give you modules that take any signature and automatically produce high quality prompts for your task in your pipeline. And to make all of this possible, we have a notion of optimizers that can take any program, any set of modules that you've connected together, and end-to-end make sure that the prompts in there or the language model weights themselves are updated so that your pipeline achieves sort of whatever metrics you are trying to maximize. So the idea at the high level is that you will be using an optimizer to compile your code, which makes language model calls, so that each module in your pipeline is optimized into a prompt that is automatically generated for you, or a new fine-tuned set of weights for your language model that fits the task that you are trying to solve. So let's sort of dig deeper here. I talked about natural language signatures. How do these look like? And these are going to replace your prompts. So as I said, these are going to tell DSPy what a transformation is supposed to do, not how to prompt the model to do it. So I have here 3 signatures, and it's that short. You have on the left-hand side a signature that just says, my input is a question, and my output is the answer for that question. I have another one that says, my input is a long document, and my output is a summary. And you can have multiple inputs and output fields. And as you can see here, what's nice about this is that, first of all, we're going to handle the structured formatting and parsing logic. You're not going to start formatting complex strings for language models, which gets messy. But much more importantly, because this signature sort of encapsulates a whole class of potential implementations, like I could prompt GPT-4 with a really good zero-shot prompt to do this. Or maybe I could prompt a local llama model, but with a few-shot set of examples that gets it to answer questions in the particular format that I want. Or maybe I could fine-tune a local model, maybe a FLAN-T5 model that's really small, in order to conduct the same signature. These decisions, these low-level decisions, should not be committed at the level of your program design. And an important factor here is that we're not giving you a small set of hard-coded names. Instead, because the language model is now our device, it's going to interpret and infer the role of these fields using their names and traces that it runs at compile time through your modules. And we're going to sort of see examples of this in a minute. The second sort of pillar here that matters a lot is modules. So once you've defined the signature, in order to actually use it in your program, you need to use a module. And a module is going to abstract prompting techniques that you might use. So in particular, it is acting like a parameterized layer. If you think of neural networks, this is a layer that could be optimized within a larger program that you're building. And it will express your signature by internally implementing a prompting technique. So some of the modules in DSPy include chain of thought. So you could say, I have this signature, and I'd like to basically attach it to a chain of thought module in order to solve this question in an effective way by thinking step by step in a way that is optimized for my pipeline. Program of thought says, I'd like to solve this signature by actually writing code and executing that program, that little program, and using the results in order to inform the output of the language model. And React is saying, I'd like to build a small agent that solves my or implements my signature by interacting with a bunch of tools that I specify. Once a module is declared with a particular signature, it gives you a callable function. So you can give it the inputs of your signature, the values that fit these values, and it will internally conduct the language model calls and give you back the outputs that you need. And what's really important here, and this is the crux, is that in order to express a particular signature, we as the DSPy developers need to worry about 3 decisions, and this is what we're going to optimize for you. Which language model to call, what prompt instructions, and what details of the prompt are we going to map your signature into, and maybe the most fundamental or powerful lever we have here is what examples of this module that we have are we going to create and then utilize in order to teach the language model, whether through few-shot prompting or fine-tuning, how to implement your signature in an effective way. So let's get concrete. This was a lot of the high-level picture, but let's get very concrete. Let's solve an interesting simple task that allows us to expose a lot of these components. So this is the task of multi-hop question answering with a data set called Hotpot QA. And you can actually play with this on the DSPy.ai GitHub repo. There's a lot of examples with this and with other tasks. So the typical structure here is that we're going to get a question, something like, which award did Gary Zukav's first book receive? And these questions are interesting in the sense that there's usually some level of indirection, right? I first need to know Gary Zukav's first book in order to know what award it received. And the task has 2 subcomponents. We need to retrieve the right documents, so in particular a document about Gary Zukav, and then a document about his first book, which is the Dancing Woolly Masters, and then we need to use them to correctly answer the question. So if you're using another tool, maybe LangChain or Llama Index or other things, you could build a simple prompt template for this task. You could sit down and say, all right, I know how to prompt GPT-4 or GPT 3.5, and I know how to get it to do thinking step by step. I'll teach it to do a chain of thought, and then extract an answer from that. And this is the prompt that does precisely this. And I could then write a small wrapper code around my prompt and extract the answers accordingly. The challenge here is twofold. First, well, you got to write this prompt where you're making a lot of ad hoc decisions about how to coerce the language model to follow your instructions. The other thing is, well, it doesn't really get you too far in terms of quality because you don't really have that much insight into the specifics of what gets the model to answer these questions correctly. You could also use an off-the-shelf chain that's already pre-implemented. So, for example, you could use a React agent that knows how to interact with retrieval and other tools. And indeed, there are open source implementations of these things that accept arbitrary tools. The problem is, whether you do this with a zero-shot prompt or a handcrafted prompt for other tasks, you're only going to score around 30% in terms of answering these questions correctly. So what I'm going to show you is an alternative to this, where we're going to use DSPy. We're not going to write any prompts by hand. I didn't write prompts internally in DSPy that solve any of this. You're not going to do it. We're going to rely on DSPy to do it. And to make things more instructive and also more realistic, we're going to build up our program in 3 stages, starting from something really simple and growing it into a more sophisticated thing that achieves really high quality. So just as a start, maybe we can build a chain of thought module in which it just takes the question, it thinks step by step, and then it outputs an answer. Before we jump into interacting with tools or retrieval or anything like that. So this is the entire program in DSPy. It's simply one module, right? It's a pre-existing module, and we give it our signature, which is I take a question and I output an answer, and then I assign this module here to my variable. And this is not a good enough module in principle for these kinds of questions because it's not interacting with tools for the reasons that we're all familiar with at this point. So in particular, if you ask GPT 3.5 this question, it often makes up the castle name it infers it incorrectly from the name of the person, David Gregory, and it simply makes up a fake number of stories for that castle. That said, it's still instructive to go through compiling this before we build a more sophisticated program. So compiling in DSPy is a little piece of code in which we will give the model sort of more details about how to take our modules and optimize them for the metric of our choice. So in particular here, we're going to give the compiler one example of our task, so a question and its answer, and we're not going to specify anything specific to our pipeline. So our pipeline might have 1 step, might have 7 steps. We're not going to worry about what intermediate outputs are needed in the pipeline. We're simply going to specify inputs and whatever our metric needs to validate, which in this case is the final answer. And for answer evaluation, there's a lot of metrics built in. One of them is exact match evaluation. We can rely on this here for simplicity. So this code will sort of internally look at the modules that we have. In this case, it was just a chain of thought module, and optimize the part in blue, where basically the model learns how to think step by step in order to solve this task. So the interesting thing here is that your language model itself is what's conducting this compilation process. So I have here on the left sort of a dummy example of this, but on the right is an actual kind of snippet from the prompt that is optimized by Llama 2 13 billion chat, which is kind of a popular open source model for answering math questions. And the interesting thing that you see is that depending on the type of data that you're working with and depending on the model that you're working with, the compiled prompt might look drastically different because what works well for a different model or for a different task could be drastically different. All right, so the question here, well, I guess we could come back to this. So let's build a more sophisticated program for this task. The program that we saw before simply relied on the language model's knowledge itself in order to conduct the task. A common lesson of the past couple of years is that retrieval really helps for factuality. So what we can do here is that we can build this pipeline. A pipeline that takes your question, calls a retriever, maybe Colbert, if you're familiar with that, which is something we built, and takes the retrieved information and then gives them to the language model in order to answer the question. So let's build that module in DSPy. If you're familiar with PyTorch, this is going to look very, very intuitive. So what we need to do now is we need to specify 2 methods. The first method is just initialization, which is where we declare the modules that we're going to use. The first module is we need a retriever, and that retriever has some parameters. In this case, how many passages we'd like it to retrieve, how many snippets. And we need a module that will actually take this context that we retrieved and generates an answer. And this is not built in DSPy, but DSPy gives us a general purpose chain of thought component. And that component accepts a signature. So we can say, I'd like a chain of thought component that takes a context, which is what we retrieved, takes the question, and gives me an answer by thinking step by step, because that's the nature of this module. And there are other modules that you could use here. Once you've declared your modules, you now define the forward method. And in the forward method, you write any Python code you want. You could use loops, exceptions, conditionals, whatever you want, as long as there, you make sure you use the modules that you declared at initialization. So here, this is a very simple pipeline. We simply retrieve a bunch of passages, and then we give these passages and the question to the generate answer module, and we simply return what it gives us. And this is, if you test that in practice, because of the nature of the questions, it's certainly a little more factual. However, it does not actually, it's not always relevant because retrieval in a single hop is not always able to answer these kinds of questions. Nonetheless, we're sort of making progress here. So let's build a design for our pipeline that will actually live up to this task. And in particular, what we're going to do is we're going to take our question and then break it down into smaller queries that our retriever can effectively work with. So we can take our question, which asked how many stories are in the castle that David Gregory inherited, and we'd like to go to the language model and say, what's a simple search query here that will allow me to find relevant paragraphs? And the language model might, ideally say, well, I'd like to know what castle did David Gregory inherit? That's a question that a good retriever should almost always be able to answer, because there is a paragraph that would say that somewhere on the web. Given that information, we can sort of go back to the language model and say, Well, how many stories are in this castle that you just told me about, which is called Canardi Castle? Another question that the retriever could answer correctly. And given this totality of information, it's very easy for a language model to sort of compose and synthesize the answer for this. Now, this is the right answer. And as complex as this pipeline might seem to be, it's entirely sort of implementable in these few lines of DSPy code. So as you can see here, we have these two modules in blue in which sort of we can build a chain of thought component that takes, potentially empty context at the beginning or context retrieved by the retriever downstream, takes a question and outputs a search query. We also have the retrievers in orange, and we have the generate answer component that will take the context we retrieved and generate an answer. And the forward function here is slightly more complex, but at the end of the day, it's simply a loop in which we generate search queries, retrieve passages with them, append them into the context, and sort of assign that context as input to the generate answer module, which allows us to finally return the response for our question. And indeed, if you simply compile that under the hood, this single line is mapped into this really high quality prompt for a local language model potentially. In this case, it's for Llama 13 billion. That teaches it exactly how to generate search queries for this task in a way that maximizes your quality. And there are many different compilation strategies built into DSPy that sort of take your signatures and modules and spit out high quality optimized prompts for your metric. I'll skip over these in the interest of time. So the questions here are, does this stuff work? And this has sort of two branches. Can we ask new systematic questions that we couldn't have asked before? And this is really interesting sort of from a research standpoint. And the answer is like absolutely, because we can now not talk about, my prompt worked or my prompt didn't, and we can say like, when I compile my module for language model L with optimizer O, the quality that I get is the following, which is a highly reproducible and just a more systematic way of getting at this. And the second is, can they deliver gains? And the answer is also absolutely yes. We built these three programs here, and if you compile them, you can see that by simply applying the automatic bootstrapping in the compiler, we can boost the quality quite a bit over simple few-shot learning. And if you take an agent and you use it zero-shot or you use it with human reasoning, this is something that you can actually outperform quite a bit by different language models by allowing DSPy to compile this. And moreover, the multi-hop program that we built, whereas few-shot prompting doesn't really take you very far, you can get into the 50s if you, in terms of quality, if you rely on automatic compilation. I said earlier at the beginning that compilation also subsumes fine-tuning, and so the same program that we have here, when compiled to a fine-tuned FLAN T5 model that is under 1 billion parameters, so you could run it on a CPU on your machine, it scores 39 answer exact match and is actually competitive with GPT 3.5 after compilation in terms of passage recall. So wrapping up, the takeaways are, let's move away from messing with the prompts by hand. Let's define these modules and these optimizers. Don't expect one language model call to solve complex problems. Divide and conquer, break down your problem into components and let the optimizer figure out how to connect them together. And if you're interested in reproducibility or just running your own programs, local models, when compiled, are really competitive. So this is all open source at DSPy.ai, and you can also find our research papers there. Thank you very much.
So pretty much what I get is like you guys are attempting with this library kind of convert the prompting engineering into an optimization task, right?
We convert the prompting engineering into?
Into an optimization task?
Yes.
So what kind of metric are you guys using to, what is kind of the loss function or whatever you guys using in the optimizer to tell so that the prompt is getting better and better until like you get the better version of it?
So the components here are, you give us a metric that will measure whatever consideration you're maximizing. In simplest cases, it's the quality of the answer, but there, we have a lot of richer stuff built in there as well. And each of your modules gives us three things we can optimize. But the two most important are what set of instructions to use at each step. So how do we take the signature and tell the model exactly what it should be applying? And the second thing, which is really key, is what demonstrations we can build that show that. So internally, what the compiler can do is it could sort of run questions through your pipeline or run inputs through your pipeline, keep traces, see what traces actually succeed with respect to your metric and achieve high quality, and then see when it uses these examples as few-shot demonstrations throughout your pipeline and what combination of them works well, which sort of converts prompt engineering into a discrete optimization problem that is something we really understand how to do well in AI. So that's sort of the short answer, but the paper includes a lot of results and discussions of these.